Howdy, everybody. Just here for day 13 of Advent of Code. Before we get started, though, just again, a thank you for everyone who's been watching the videos and commenting. I'm always looking for feedback if things are going well, things that I could improve on. I'm glad to see that people are enjoying it, right? Like, my goal of this is to just try and share my previous experiences and this experience in doing this, and hopefully it'll help you guys. The goal is just to lift everyone up, make us all a little bit better at programming. And obviously one of the fun ways to do that is via Advent of Code. These little programming challenges are kind of fun. They don't always translate directly into, here's real life programming, but it's fun to, maybe learn a new language or learn a new algorithm, or hone your skills, fine tune whatever you're doing. And so I'm glad you could all join me for the ride. I've had a couple people say, hey, could you talk about this or this thing I do? I do plan to work on other things besides Advent of Code, right? But obviously for the next 12 or more days, I'm going to try and do the Advent of Code every day. And then once we're done with that, yeah, if you have ideas on things you'd like me to talk about in the computer science field, whether it's programming a language, maybe you want me to do a code review of a package you've written or something like that, I'd be happy to do that. So just send that information into the comments. So with that, let's get started and start looking at day 13. So for day 13, the idea, we're back to dots and hashes, which was in day 12, if you remember. Not nearly as hard, though, as day 12. The idea is you're given a grid like this, and the goal is for you to find where the mirror is placed. The problem says is like you've got some ash and you've got some rocks, which are the dots and dashes, but like there's mirrors that have fallen down. And so you're given this like grid, and you want to find where the mirror is placed. So the idea being you would see an actual reflection on the grid. And it describes how that looks in here. So, but I thought maybe I would just kind of show you using a Jamboard how this might look. So here's the two example solutions. And one of the gotchas, or one of the things that I had to pick out to make sure I understood the problem at first. It took me a little bit of time to understand what it meant by a reflection, because there are reflections here, right? Like if you look at this first grid, these two right here are a reflection. And if you even go further with that, even this group right here is a reflection. But what it wanted was a perfect reflection. And what I think what it meant by that was, I want you to look for a reflection that spans the edge, right? That goes to one of the edges. Otherwise, it wouldn't be a complete reflection, right? And so there, it does say that in the thing, and I added some comments in my code that describe that, but it's looking for a perfect reflection, meaning that one of the sides of the mirror goes to the complete edge. And so what does that look like? This one is not a perfect one because it can only go this far, right? But if you do some more searching, you eventually find this reflection right here. That is this part right here. And so why is this one perfect? It's because if you it might be easier to do it with this. If you like draw a line right here, this thing folds in half, right? So this side, if you flipped it over, is identical to this side, and it hits the edge. So in that case, it's it's the definition of a perfect reflection for this problem. And so it's not only vertical reflections, it's horizontal reflections, right? So on this side, there's actually a horizontal one. And you can when you're visualizing it, when you look at it, as you start to notice, you can see like there's a clear delineation right here. And that's where the reflection is. And you can see we go down 3 here to the edge, and we go up 3 here to the edge. And so the mirror is reflecting across this section right here of it. So when you're thinking about how to solve this problem, for part one, it seemed like, okay, I don't know of any, like, there might be some kind of, like, when you think of what's happening here is you're kind of doing a palindrome sequence. There may be some way for you to say, like, what is there's a thing called, like, a largest palindromic sequence. That's a programming pattern that you can use. There's also the smallest one, or I think it's just the largest. You're usually only interested in the largest. You could potentially use some of those solutions here, but because we're already in a grid system, it seemed simple enough to me to just say, hey, if I'm looking at columns or I'm looking at rows, can I find adjacent columns that are next to each other that are equal? And then can I, like, work my way out and see if I can get to the edge of the thing with those equalities? So what does that look like? You start, like, you just start over here at this first position, and you say, hey, is this one and are these two equal? No, they're not. So you're going to move and you're going to keep doing that, and eventually you get to this position right here, and you say, are these two equal? And yes, they are. So now you kind of know where a potential midpoint could be. So your goal from this point is to start checking outwards and making sure they're all equal, right? So now you say, is this one and this one equal? And if it is, you keep going. You say, is this one and this one equal? And if it is, you keep going. This one and this one equal? It is, you keep going. Now you're at an edge, so you know you've found that position, that midpoint, right? The problem then is once you found that, or like the solution, they say, is once you found that, you basically just need to do some math to summarize them. So the goal is, like, now that you found this midpoint right here, it's at 1, 2, 3, 4, 5, right? It's at this fifth one. That means that you're at column 5, and for all the columns, you just add that number. If you find one in a row, you add that number multiplied by 100. For this solution, right, we found it at 5. If you do that same algorithm, you kind of walk down. Eventually, you find this is the midpoint right here, and you do that same thing. You check these two, they're the same. Then you check these two, they're the same. Then you check these two, and those are both identical. Those are all identical. And now you've hit an edge. So you can say, oh, that is a perfect reflection. I found the solution. And in this case, it's 1, 2, 3, 4. It's at this fourth position where it starts. So because this is a row, the answer to this one is 4 times 100. Whereas because this one is a column, it's just 5. So the total solution of all of these is what it wants you to return. 400 plus 5 is 405. 405. So that's the answer for, like, these two columns right here that it was testing in the example. And that's kind of the algorithm that I used, again, to get to this, right? Is figuring out this number and this number is just a bit of math once you've found the middle point. The goal is, can you find, the real meat of the code is, can you find that middle point, and can you verify that it's a perfect mirror, meaning that it reflects all the way to one of the edges. And they spend some time explaining that. You kind of get that if you read all of the information. You say it doesn't have to expand through the whole thing, right? First of all, this is like an odd number of columns, right? Or you could get odd number of columns. And so there's always going to be, the potential for there always to be, like, one left out, right? If you get an even number of columns or an even number of rows, then you'd expect it to, like, expand in both directions. That turns out, though, if you think about your algorithm, not to be necessary, but I'll show you that in the code, right? Just, again, at a high level, what are you doing? Trying to find a pair that is equal, and then work your way outwards and see if each of those pairs are then equal as well. And you do that until you reach the end. And if you've done all of those, you know you found the quote-unquote perfect reflection, and you know where that point is. Okay, so let's look at that in code. For this case, I had started, I thought, oh, I can use nom to parse this, but because you're literally just using a grid system, and I used characters, I suppose you could turn them into bytes and stuff like that, or integers or whatever. I just used characters, and so I just used the I implemented from for a note to do that, and so all I had to do is to split by double new lines. So the input looks like this. If you split by double new lines, you're now going to get like this for each of, you're going to get this for each of your notes. And so you just need to be able to parse that. And so what does that look like in code? If we go back up here to our parse function, or our from function, that allows you to use that into method, or our from implementation, I should say. Given a string, you basically just split it by lines, and then for each of the lines you split it by characters. You get the characters and you collect those two. So what do you end up with is this grid of characters, which is a 2D array, right? You get a vec of characters. You get this 2D array. So now you have this 2D array. You can kind of like reason about rows, or reason about columns, or reason about rows, and say like, are these two equal or not equal, and implement those. And that's what part one looks like, right? Is now that I have these notes, I can just call this find the reflection point, right, on that thing, and do that for each of my grids, each of the grids that I'm given, each of the notes that are there, and just add those values together. So what does this part one reflection look like? Let's go look at that. I created some helper functions that maybe weren't totally necessary, but made the code look a little bit cleaner. I asked the question, are these two rows equal? So if you give me a y1 and a y2 position, or I guess it's this way. If you give me like a y1 and a y2, I'll tell you if those two rows are equal to each other. That's simple enough. When you have a grid, you can just say, hey, is this vector equal to this vector? Rust will do that for you without an issue. Most programming languages will do that, right? Are these two lists equal? That was a pretty easy thing to do. The columns are slightly different because now, remember, you're going over a span of rows. So you kind of have to do this one character by character. There might be a way to do this where you're like collecting all of the column values from each thing, and then you can do an equal. But this felt simple enough for me. Basically, again, I'm going through each of the rows, and I'm checking if at that, if the X and Y positions within those rows are equal. So if I ever find one that isn't, I know that the columns can't be equal. But if I've gone through all of the rows in for those two columns and they're all equal, then I now know that those two columns are equal. If you need visualization for that, is remember, these are the rows. These are the rows right here. And so as I'm checking if the columns are equal, like if I'm interested in these two columns right here, like this one and this one, for each row, I'm just going to say, are these two equal? Are these two equal? Are these two equal? Are these two equal? And obviously, when I find one and it's not equal, then I know there's something wrong. Or it's not, the two columns are not equal. Okay, I'm going to try and clear out most of this stuff so we can, it'll be useful for part two. But having those two helper functions, now I can reason about my initial implementation relatively easily. Basically, I just go through each of the rows and I ask myself, is that row and the row next to it equal? Right? You'll see a lot of -1s, -2s, +1s in here. That's just array math, right? I'm going from, I'm tracking like values. I'll try and describe those as I go in, but I want to iterate through all the rows, and I want to test if the row after it is equal to this row. And if it is, now I have a potential middle point. So I can see if from there I can like work my way outwards and find that. So how do I work my way outwards and find that? Really what I want to know is how far do I have to go? And so I want to find the min distance to the edge of the graph, right? So if I'm if I'm right here, I want to find out how far do I have to go out in each direction to verify that they're equal. And I know I need to go 4 this way. I know I need to go 5 this way. The only way that that's actually going to work then is if I go 4 out this way and 4 out this way. So the min distance is really just the minimum of those two values, right? So what is the min of this one and this one? It's 4. And so I know I need to check out 4 this way and check out 4 this way to get to verify that it is a perfect mirror in that sense, right? And so then I just do that for each value from in that thing I want to check. Notice I do 1 here. I don't need to check the two middle cases because I've already checked those at this position. So I just need to check the outside ones and go out, right? But then I just say, hey, are those 2 rows equal? Again, you had to do a little math here to get to those positions. What is this math showing though? Is like, if you look at the grid, I'm saying is the row minus the distance and the row plus the distance plus 1 equal? And why do you do that is when you're iterating, you're technically at this position right here, right? That looks really ugly. This is what variable did I use? I. So this is your I value right here. And you checked I to I plus 1. But now what you want to check is this one and this one. Well, this the midpoint is actually right here between I and I plus 1. So if you're wanting to go this way, you need to add the delta plus 1, right? Notice the plus 1 here. You need to add the delta here. So that's why you get I plus D plus 1 here. And then here you can just go I minus D because you're just going back this way, which is where the ith position is. So that's why that math looks a little funny. But if maybe that's confusing you, again, the only thing that you're trying to do here is just test if I found 2 rows that are adjacent to each other and equal, now I want to check the rows after those and see if they're equal or outside of those. And I want to keep doing that until I've made sure that all the rows all the way outside to one of the edges are equal. That's what these two things do, right? So again, one last time, when you're doing this, you're going to test to see if you find columns and if you find rows. I think I was talking about rows. Sorry if that's confusing. I'm actually illustrating a column right here, but the algorithm is actually the same, and maybe I can show you that. The difference is just what is the value that you return of the reflection. So after you've checked the rows, you want to check the columns too, and that's just the same thing, but now you're working on columns instead of rows, but you do the same math, right? You still, the only difference between this code and this code up here is you're calling for rows, you're calling rows equal, and for columns, you're calling columns equal. And obviously the iterations that you're doing are slightly different because now you're dealing with each column as opposed to each row. And that would be something like maybe to make sure you're checking if you're doing this yourself. They weren't always square, right? They're not always a square grid that you're getting. Some of them, they're rectangles, right? And so sometimes the length and the width may be different. And so here I'm checking the length of the number of rows, and here I'm checking the length of the number of columns that go through, any one row. But it's all the same, right? And we just say, if it's a row that I found, now I'm going to return that value plus 1 times 100. Again, y plus 1. We're doing indexing in arrays. So this is the 0th value. This is the first, second, third. But if you look at the problem, they're labeling them grid 1, 2, 3, 4, 5. This is a common thing, right, in programming. I'm sure you're all aware. Sometimes they treat the first one as 1. We all like to treat it as 0 for legacy reasons, barring a few special languages. So you just need to add 1, times it by 100. If you find a column, you just add 1. You don't need to times it by 100. My guess is why they did these two different things is so it was clear that there was a difference between the rows and columns you found. There's potential for you to like find false reflections in different places and get them wrong. This helps clarify that, oh, I found a value in the row and I found a value in the column. So when you get the sum of the answers, if you had like not found them correctly, you'd be able to potentially go back and see why you got it wrong. Okay, but that was essentially it for part 1. Again, just to reiterate, we're going to go through each of the rows and each of the columns, and we're going to try and find that midpoint of the reflection, and then we're just going to work our way out. And the way we work our way out is we calculate the min distance to the edge, and then just and work our way out until we hit that edge and make sure all of them are equal. If we ever find one that's not equal, we know this can't be it, and we can keep looking. Once we found it, though, we can return the value of that reflection. You might argue that this was a brute force approach. There may be a better solution that is technically faster. This felt fast enough to me, especially given the problem set. That's something just to be aware of in general, but for these puzzles, look at the input sizes, right? None of these grids were particularly big compared to the test case, right? Like as you're scrolling through here, you see none of them are especially large, right? So the value of n, which is like n and m or whatever, the length and width, are not going to be large. And so for each iteration or for each check, you're only ever going to be doing, say 10 by 20 or whatever. No single calculation is going to require more than like 20 checks, I guess is the way to say it, plus the number of like checks you have to go outside the grid, which is some, like n over 2, right? Probably even smaller if I thought about it. But just to come back to it, the idea is, I think in these type of cases, a quote unquote brute force solution is probably okay because the input size is small, right? If these grids were super huge and like there was the other day, if you go from like a small set to like a real large set that you have to check, and your checking is like exponential, then you start have to looking for better solutions. But it didn't feel like this way for part 1, so a brute force solution seemed okay. And I imagine I always like to go look at everyone else's solutions. Most of them will look like this. Again, you might find some people that have done similar things before where they find some like kind of palindromic sequence, the largest palindromic sequence. That is a problem that you'll see in other programming places like LeetCode or those equivalent type things. Those do have potentially faster solutions when you're dealing with like large sets. But in this case, nothing was particularly large or complex. And so, again, I think brute force was the way to go. How does that look? How does it change for day 2? So once you figure it out for day 1, they actually say, oh, just kidding. There's a smudge on the mirror, and exactly one of the dots or hashes are the opposite. So what does that mean? And note, there's exactly one smudge. So exactly one of the dots or hashes are actually the opposite type. What does that mean is it's saying if the smudge was right here, or let's say the mirror was right here. Well, let's just do it the way that this was. The mirror is like reflecting on right here. There's a smudge now right here, so this actually becomes a dot instead of a hash. Now this is not a perfect one, right? And it doesn't work. It turns out what changes for this solution is, the way to think about it is the smudge is actually right here. So this becomes a hash. And now the sequence or the mirror is right here, right? Because now you can reflect these ways and you get a larger, better value. And um, I'm trying to think of how to describe this. Sorry. That you might say, oh, well, that actually doesn't change my vertical value, right? Like, technically, there's still a mirror right here, right? This could still potentially be a mirror because it reflects outward. But now this one reflects outward too. And it doesn't really say this directly, but it implies that like what you're actually interested in is like the larger values, meaning you want the rows first, and that changes the way the reflection works. And so that's why you're doing rows to columns. But the idea being is if I if I do it this way, I'm only going to get a value of 5. If I do it this way with this smudge, now I get a value of 400, right? I think, is that right? Something along those lines. Is that right? 3 rows above it. Yeah, the 1, 2, 3. You get a value of 300. Sorry, you get a value of 300. So as opposed to getting 5, now you get 300. It's kind of telling you want to pick that larger number. I think, though, if you look at the patterns and the way I solved it, you can actually implement it the same way I did, just ignoring this case now. You say, oh, if I found one where there's no smudge pattern, I can solve that. And let me talk about how that solution works. It's actually quite the same. But I think a lot of people will probably confuse this adding a smudge to it and maybe try and implement another way. My solution does work. It solves the problem. It just may not solve it for like the general cases, right? Because again, the smudge here doesn't actually affect that this could be a mirror as well, right? Because it reflects here and it reflects here. But switching these two now makes it reflect here, which is much larger. And so thinking about the way to solve the algorithm is you want to actually go this way, try these ways first, and then try these ways. And that will get you the answer to part 2. So if you're, I don't actually think I have the code for it anymore, but I originally tried a naive solution for part 2 where I said, what if I just go through each of these and switch them and see if I get an answer? And the first time I get an answer, then the problem is solved. That doesn't actually work because, or that doesn't get you to the right solution. At least it didn't for me. I could not get the right solution doing it that way. And so what I had to do then was say, okay, well, how do I determine the mirror, the mirror if there's a smudge on the mirror? And maybe that's the way to think about it. The key point is there's a smudge on the mirror. We know there's a smudge. There must be a smudge. Sorry, I'm doing this in my head now. It actually makes sense to me. All that talk the last 2 minutes is not correct. We know there is a smudge on the mirror. So this one can't actually be the mirror because in order for this to be the solution, there would have to be a smudge on it. But we know there is no smudge on it, so that can't be the solution. Right? That cannot be it because there's no smudge. So what we want to find one that has a smudge, and that's how my solution actually works. So there you go. I may have been like, sorry, I did this and then I had to go to some meetings and now I've come back. Let me just look really quick and see. Yeah, there's the difference between the two sides of the reflection are 1, right? So that's why my solution for part 2 works as it does. Originally, I was thinking there was some issue with the input, but that's not actually the case, right? This one does not work because it doesn't take into account that there is one smudge on the mirror, and it says that in the advent of code. So you're looking now. What you're doing is, let's just talk about the problem too. You're now looking for a solution where there is a smudge. There's exactly one smudge. And so this one happens to be it, right? This is where there is the smudge. What you wouldn't, again, why this way doesn't work is because there's 0 smudges on it. And you might find other solutions in there where maybe like, oh, I can make it if there's 2 smudges. Excuse my terrible writing. That doesn't work either. You want to find one where there is exactly 1 smudge. And so how does that look? It's actually not much different from my P1 solution, right? So to reiterate, my P1 solution was to find that midpoint and to work your way out. Well, I want to do the same thing, except now I want to allow for some like tolerance. I want to be able to say, hey, I want to work my way out, and I want to find where, and it's okay though if there's a difference, as long as there's only a difference of 1. So how does that look? My column equals and row equals are now slightly different. I'm going to call row diff functions now instead, right? And what these calculate are the difference in between the 2 rows or columns. So as opposed to just saying, are they equal? I want to know how different they are. And the way that you do that is you just keep a counter and you say, hey, for each of, go through each of the values. And if either of them are not equal, I add 1 to my delta. You do the same thing right here for the columns. You just go through each of the values in the columns for each of those columns. And you say, hey, if they're different, I add 1 to my delta. So now for part 2, I can kind of, I'm going to use the same general algorithm, but instead of saying, are they equal, I'm going to just track the diffs. So how does that look in the code? For each row, I go through and I say, hey, what is the diff between my row and my adjacent row? And I say, if it's less than or equal to 1, now I have a potential mirror between the 2. And I just do the same thing, right? Now I want to calculate the distance to the edge. And for each of those distances, I want to do a diff of those rows, right? Now, instead of saying, are the rows equal, I'm going to say, what is the diff between those rows? I'm going to add that to my diff total that I'm kind of tracking. And I know if I ever get to a place where there's more than 1 different, then I have failed. This can't be it, right? Once I've gone through all of them, though, I now know I have a potential solution. But yeah, here's the thing. This is the part I'd forgotten about when I was explaining it before, right? Every mirror has exactly 1 smudge. So since there must be a smudge on the mirror, if you happen to find a solution through this and the difference is 0, that can't be the answer, right? You need to have one with a smudge in it. So you want to keep checking at that point, right? If you've gone through all this work and you get to here where the diff is 0, you've essentially done the same thing as part 1, right? And that's not what part 2 is saying. Part 2 is saying there needs to be a smudge in that mirror. And so that's what this check is here. Again, you could potentially optimize this in some way by just tracking if the diff is greater than 1 and stop. Maybe you can't do that. But the idea is, again, at a high level, you're doing the same like loop as part 1. Go and find the middle point and work your way out. You just need to now track the differences. So I want to, and you do the same thing for the columns, right? So part 1 and part 2 both are the same. Start with the rows, try and find them. Start with columns, try and find them. Eventually you find one that is a mirror, and once you do that, you can return those values. Okay, so let's kind of step through that when we're doing this again, right? When I'm testing this row right here, or this split right here, notice the differences between these 2 are 0. So now I can do my check, right? That's what this part of the code is doing. It's saying, hey, what are the diff between those rows? It's 0, which is less than 1. So now I can check the min distance to it, and that happens to be 1, 2, 3. 3, this is the min distance, right? So this one's 3 and this one is 4. So I'm going to go 3 up. So I know my range is going to be here to here. And now I just want to calculate those min distances all the way up and down, right? So this is 0, this is 0. Oh, these ones are different. This one produces a 1, right? These ones have a 1 difference. So now my total difference here is 1. I know that's the solution now because it has to be exactly 1. If I was going through and I was calculating, you know, this right here, again, I'm saying this multiple times, this would not be right because there's no smudge. So I did get there, apparently. I just forgot it in between my meetings. Sorry, these 2 days, I have like these, they call them planning meetings, where I spend 2 days doing all this planning and stuff like that, and it kind of drains my brain. So these next 2 days may be kind of funny in me not remembering all the stuff I go through. But just to reiterate it one more time, part 1 is, can I find that midpoint and work my way out and see if it's like a perfect mirror? And part 2 is the same, except for now I want to have some kind of tolerance, right? And I want to make sure I can find that same thing, use that same algorithm, but find one where there's exactly 1 different position between the 2 sides. And the way you do that is, instead of saying rows equal, you just now do rows diff or calls diff, and you just kind of track that difference. And you know, if you've ever gotten more than 1 difference, it can't be it, so you can move on. And after you've gone through all the rows, if there's literally no difference, you know that can't be the answer either, so you move on as well. I don't think there's a way to like optimize this part anymore. Like I said in part 1, there's a potential for you to solve it via like a longest common subsequence. I didn't do it. I haven't even tried it, so maybe it isn't actually possible. Longest palindromic sequence, I should say. I don't know if that's an actual way to solve it. Maybe it is. If you solved it that way, I'd love to see it. But for part 2, well, I suppose you could still solve it that way by like doing like an edit distance type thing with your palindromic sequence. Like, it's still a palindrome if you only have to make like 1 edit as you're doing the palindrome. So you could potentially do part 2 with that. This just felt easier, and again, the input sizes were small, right? Like, most of the grids were this size. None of them were like 1,000,000 times bigger, and part 2 never became, oh, it's 1,000,000 times bigger, right? If you think back of day 2's solution, using something like dynamic programming was important because you would, if you tried to brute force switch all the values and see if that produced like a correct solution, that worked maybe for small sets, but it doesn't for very large. This didn't happen to be that case, and part of that is just reading and understanding the problem and looking at the input size and saying, hey, do you know what, there's actually not that, this problem set isn't actually too big. There's a potential for you to have, I don't know why my part 2 naive solution didn't work. After I solved it this way, I tried to do it the naive way, where I said, hey, let's just switch one of the values. I think I had mentioned this earlier. Like, the idea is, what if I turn this into a hash? Does that produce a mirror? I never got that to work, and I wonder why it is. It didn't produce the correct results. It's probably because switching one of these, I just literally switched one of these and then I called my P1 reflection on it. Probably what I had to do is have some kind of more complicated knowledge of it. Again, because the trick that you had to pay attention to was there was exactly 1 smudge on the mirror. So the idea being is, like, if you switch this and it gave you a solution, but this wasn't part of the mirror, then that is not a valid one, right? Like, say you switch this one and the solution, the mirror is like right here, right? That would not be a valid solution, but I guess my naive thing would not have checked that. So I think in the end, the way that you get the best answer to it is just to do what I did, right? Is you say, I'm going to start somewhere. I'm going to start somewhere in the middle, or I'm going to start checking values that are adjacent to each other and find this potential middle, is what I should say. And then I'm just going to kind of work my way out until I reach an edge and make sure those are all equal. And then if you do that, part 2 is not hard. Remember, I essentially use, you could potentially turn this part 1 reflection and this part 2 reflection into the same function, just where instead of doing rows and columns equal, you're doing rows and columns diffs, and you're tracking those. Or you could say, like, what is the diff value I'm looking for? And for part 1, the diff would be 0. I'm looking for a 0 diff. And for part 2, I'm looking for a 1. And so you could potentially combine these. That's how similar the algorithms were. I didn't do that. I kind of left these out. Maybe later if I come back. Or you guys could try and do it. How would you combine these two? That would be interesting to see how you'd combine them. But again, if you're using this pattern where you kind of find a potential middle and then fan out on both sides and see if those all match for part 1, the part 2 implementation actually doesn't change that much. You just say, well, now instead of them being equal, I'm just going to track the diffs, right? And as long as the diffs equal 1, I know I found my solution to the problem for part 2. So there you go. There was day 13. I feel like it wasn't necessarily as hard as day 12. I don't know. Maybe some of you are better at dynamic programming than I am. I took that course and I felt like that helped me a lot in understanding dynamic programming. But this one it felt more straightforward, right? Is just at least for me. So I would. I think this is the thing. I had mentioned this in a couple of the subreddit threads. People were saying like, oh, day 12 beat me up. Do I just quit? The answer is no, don't quit. If you can't solve a day, that's okay. If you go back and look at my previous years, there's days that I just never got, right? And time went on and I haven't had time to go back and try and work on them. Keep working on them, because some days are easier than others. Sometimes you will know what the answer is or what a general algorithm might look like, and you'll just be able to solve it. And some days you won't, and you'll need to spend more time doing that research, doing that, looking at other people's solutions, kind of finding ways to solve the problem in a different way. And some days you'll just get this where a sort of like brute forcey approach works and it solves the problem. And that's the only thing. So if you think at a high level, like what is the trick to day 13? At least for me, the trick was, can I understand and read the problem? And this happens a lot in most programming, right? Is you have solutions, or you have some business person come to you, or some person that wants you to write a program, and they give you like a list of things that they want that program to do. Understanding the details of that actually can be important, right? So in this case, I think that's what this was for day 13. Once you figure out how to solve it, it wasn't particularly hard. You just had to key in on some values of like, the mirrors have to be perfect, right? That was one of the places in here. It's a perfect mirror. And what does that mean is, if you look at the examples that they're talking about, that perfect reflection means that it reflects all the way to one of the edges. For part 2, the idea was there's a smudge on the mirror, and there must be a smudge on the mirror. And so if you didn't get that there must be a smudge on a mirror, right? You discover that every mirror has exactly one smudge. If you kind of glossed over that, you probably don't get the right answer, because now your original solution won't actually work, right? They kind of say it right here. The old reflection line won't necessarily continue being valid after the smudge is fixed. The reality is it won't be, right? Because your solution to part 1 meant that there was no smudge, right? But now you know there must be a smudge, and so that original one wouldn't be it, right? And so picking up on those key things in puzzle solving, I think, is important. Right, like, just to be honest, those things got me as I was doing this. Maybe some of you didn't have that problem, you saw them right away, but those things got me for a little while. This part kicked me for a little bit, where I was like, oh, why am I not getting the right solution? I'm doing this work that should logically work, and it didn't occur to me until I was like actually looking at at like at one of the grids that I said, oh, um, this mirror has 0 diffs in it, but it talks about there being a smudge. There must be something to that, and sure enough, it was. Every mirror has exactly 1 smudge. So don't beat yourself up if you get that. I'm sure if you start looking through some of the solutions, people are like, right, like there's always gotchas. We all have little things that we miss that we spend a little bit of time debugging. Just keep pushing forward and keep trying. Reread the problem if you need to. Maybe look for different approaches to the problem. You'll eventually come to solve it. So don't be disheartened. Like I was saying earlier, just because one day is hard doesn't mean another day will be harder. And you may find that some days are easier for you than other people, or that some days are harder for you than the average person. Don't be discouraged by that, right? The goal of Advent of Code is just to have fun. If you don't solve them all, no one's firing you, right? So make sure you're having fun as you're doing this. You're just trying to solve problems. And anyway, I hope you guys liked my solution to it. I'm interested to see how maybe you would optimize it, if you have any thoughts, or potentially how you implemented it. Did you do another way? Maybe you could describe it just in general, how you solved it. And after we go through all these days, some of my videos could be potentially looking at other solutions and how mine could be optimized or work better or whatever. So again, I have a lot of fun doing this stuff, and I want to keep doing it, partially for myself because I like to solve these problems, but I also like to learn and grow. And so you guys giving me input, I always like to love, but I also like to teach and help people, right? Part of the job that I have right now is mentoring and stuff like that. And this is kind of a way for me to do that at a different level than what I do at my normal job. So there you go. That is day 13 for Advent of Code. Talk to you guys tomorrow.